with the addition, subtraction, multiplication, division, and we had just started talking about, how to calculate the domain for these functions. So I actually wanted to continue that discussion. So let's look at some examples here again from our homework. Okay, so hopefully you can all see this. So we've got two functions, f and g, and they're basically asking us to find what the equation for g divided by f would end up looking like. And then, of course, they're also asking us to find out what the domain of this function is going to be. So again, that order is going to be important. So you can see we have g as the function on the numerator, f as the function on the denominator. So basically when they give us g divided by f evaluated at x, remember by our definition, that means you are taking the g of x function and dividing it by f of x, right? So our g of x is defined as x minus 7. That will go on the numerator. The denominator is defined for the f function, which is square root of x. And honestly, that's all you have to do. Now, I am not sure if they want us to rationalize the denominator, and rationalize the denominator basically means, do they want us to get rid of that square root in the denominator? So what I'm actually going to do is I'm actually going to go ahead and type this answer in and see, what my MATLAB says. And if they don't accept our answer, then I'll show you how to rationalize our denominator. So we are doing x minus 7 on the numerator, and then square root of x on the denominator. I'm actually not sure if they want us to put parentheses. So just x minus 7 on the top, square root of x on the bottom, and we'll check our answer. Okay, so it looks like my MATLAB is okay with us not getting rid of that square root of x from the denominator, leaving it there as it is. So it may be just, where they're just asking us to find what the equation would look like. They're not having us do that. Now, the second part of our question is, of course, asking us to find the domain for this function. So let me go ahead and clear this part out. So they are asking you for the domain based on this g divided by f function over here. So any ideas on what do you think the domain for this function would end up looking like? What kind of restrictions are we seeing on our x variable here?
It can't be 0?
It can be 0. Yeah, because what will happen when we have our x value as 0? So let's just think about that. If we make x as 0, that would of course end up becoming 0 minus 7 on the top, square root of 0 on the bottom, and then of course we would end up with division by 0, right? And we don't want that, because again, guys, remember, division by 0 is undefined. So that's a good start. Very nice, Arthur. What else do you guys think? What other restrictions could we have on our x? Okay, so let's think about it this way. How about we take the original function f of x and the original function g of x, and let's talk about what their individual domains are going to be. So does somebody want to tell me, what do you think the domain for the f function should be?
Would it be negative infinity to positive infinity?
Okay, Braden, so you are saying negative infinity to positive infinity. So let's think about that. So what do you think happens with the square root of x when we start putting negative numbers in there? Somebody's got to remember that, right? What did we say for square root functions?
They would become irrational numbers.
No,
Wanna-
imaginary, right?
Mhm.
Because they would end up becoming imaginary numbers. And remember, domain is always in terms of real numbers. So Braden, what's going to happen is we actually will not be able to use negative numbers, right? Because the moment we put a negative inside that square root, you're starting to look at imaginary numbers. So the restriction for the f function is going to be you can start at 0 and you can go to infinity, because 0 with square root of x, of course, will just end up giving us a 0 answer, and you can have all positives in there. Now for the g function, which is x minus 7, what do we think the domain for that function should be? Do we have any restrictions in that? No, right? So we can use all real numbers. So negative infinity to positive infinity. So again, guys, if you remember, when we talked about the domain, and I know I've kind of got this overlap over here, but basically whenever we are talking about the domain of these operations with the functions, you are looking at the intersection between the domain of each of those individual functions. So if we go back to our example over here, the intersection between these two domains would basically end up becoming, just a second. So with both of these domains, our intersection would actually look like so if we just talk about the intersection, that would actually have 0 to infinity, including 0. But as Arthur pointed out earlier, we cannot use 0, right? Because that's making our denominator become a 0, and we cannot divide by 0. So the only modification we are going to end up doing then is instead of including that 0, you just don't include that 0 for the final domain. So the domain for our g divided by f function is going to end up becoming 0 to infinity, not including 0. So let's go ahead, put that answer in. Where's my infinity? There we go, and check. Okay, and there you go. So any questions on this one? So like I showed you, when you're going through examples like these one, go ahead, find what your individual function domains would be, see what the intersection comes out to be. And then in this case, of course, the intersection itself did not work since we could not include our 0. So we ended up, instead of using a bracket, we ended up using a parenthesis. So practice with that a little bit. And, of course, if you have any questions, let me know. So that was example on just kind of how to calculate domains, and especially when you are looking at division. Now, the next example I wanted us to look at, okay, what happened here? There we go. Okay, so this is actually where we're getting into the second part of our 2.4 section over here. And this is where we actually talk about composition of functions. So again, if you've seen the video for this, then you will be familiar with the idea of composition. But in this case, what happens is you are, in a way, creating a whole new function, kind of like the operations with functions did. But in this case, what we end up doing is we take one function and put it inside of the second function. So it's always the outer function and you have the inner function. So of course, the inner function is what's being put on the inside. So basically, if you have a composition which looks like f of g, which is this guy over here, and you can, again, obviously see the definition here, but this is kind of the notation that we use. So you have this little open circle. So yeah, it basically does not look like multiplication. It's more of this little open circle you have. And the way we write it out is in this format, where the first function becomes your outer function and the second function becomes the inner one. And the idea is you take this g of x function and you have to literally place it inside of the outer function. And then, this little illustration that we have over here kind of shows you how the domain and range of these composition of function works out to be. So I actually wanted to talk about this in terms of an example, and then also, highlight kind of what happens with the domain of these functions kind of thing. So starting out with a simple example over here, you can see we are talking about composition with f of g of -3. If we had to use our little composition symbolism, that would be f of g evaluated at -3, which ends up becoming f on the outside, g on the inside at -3. So the first thing we are going to do is start with the inside function, g of -3. So you are going to take g, evaluate that -3. So let's start with this guy. What do you think g of -3 will come out to be?
It'd be 9 minus 2.
Yeah, because your x is -3, right? So you've got x squared, which will end up becoming -3 squared minus 2. So -3 becomes +9, minus 2 becomes 7, right? So the idea is this 7 is actually now going to become the input for the f function. So now we will say, okay, this equals f. G of -3 came out to be 7. So you're actually going to put 7 in here. And now for the f of 7, obviously we will go to this function over here now. And what do you think f of 7 will come out to be?
6.
Yeah, because that's x minus 1, right? So that will just end up becoming 7 minus 1, which gives you 6. So the way composition works, and this is kind of how one of my professors used to describe these composition of functions. He would say, think of these as meat grinders. He's saying you're putting the meat in, as a solid mass of this chunk of meat. And, by the time the machine does its thing, it comes out, you have ground meat. So that's kind of what's happening. We started out with the -3, which went into the g function. So that was our starting point. It did its math, and then it went into the f function as 7. Then f of 7 did its math, and by the time you came out, you had 6 as the answer. Now here's the thing, guys. When you write these ordered pairs, remember the first number you started out with was actually -3. So that's your x value. By the time we did our math and came to the final answer, 6 was your final answer. So -3 was that chunk of meat you started out with, and 6 is, that ground of meat that you get at the end of it. So that's kind of how these composition of functions work out to be. So in the answer box, you are obviously typing in the final answer, and our final answer was number 6. And that's basically what we are doing in these composition of functions. Now, the one other thing I really like about your illustration over here is that's basically what it's showing you. You started out with the x value, which was -3 in our case. We put it in the g function first, and we did the math, which basically ended up giving us the answer of 7. Then that answer 7 went inside of the f function, and by the time we did that math, we ended up 6 as our final answer. So that's kind of how this illustration works, and I really like how they kind of show you, how you move in steps in that case. Okay, so that was just with, starting out with a given number, but let me show you another example over here with this guy. Oh, wrong one. There we go. 37. That's the one we just did, this guy over here. Same thing, composition of functions, but this one is actually going through 3 different functions. You can see we're starting with G, then H, then F. So let's take a look at this guy. So G of H of F at 7 is going to translate into G as the outer function. Then the second function is H. And then our innermost function is F, which is being evaluated at the number 7. So the way you're going to start, again, from the inside, we work our way outside. So start with F of 7 first. So that means where's our F function? We'll be doing F of 7 first. So what do you think F of 7 will end up giving us?
$55.
55, yeah, very nice, because you have 7 times X, which also happens to be 7, plus 6. So of course that's 49 plus 6, which gives you 55. So now this 55, remember, is going to become the input for the H function. So that's again G on the outside, H on the inside, but now we are replacing F of 7 with the answer 55. And like I said, this will now become the input for the H function. So now we are going to be doing H at the value of 55. And that's, of course, this function right over here. So what do you think H of 55 will come out to be?
7?
Yeah, it's kind of funny because they're giving you X minus 6. So of course that's 55 minus 6 divided by 7. So literally you are almost undoing what the F function just did, because you're doing 55 minus 6, which would be 49. 49 divided by 7, takes us back to the number 7, which is okay. That's kind of how I think they designed this example. So now you will take that 7, which will become the input for the G function. So now instead of H of 55, you will have 7 over here. And then, of course, that's your last calculation, G of 7. And what's that guy?
54.
54, yeah, because again, we are doing 7 squared plus 5, which is, of course, 49 plus 5. And you end up with 54. So again, if you think about this ordered pair, we started out with 7 as the first number. By the time everything was said and done, you ended up with 54 as your final answer. So let's type that in again, 54. And there we go. Did anyone have questions on these 2 composition examples we just did? Okay. Alrighty, so this guy, let's go ahead and clear him out, and let's look at okay, so this is actually a different take. They're still asking us to do composition, but let's take a look at the way they're defining this. So you can see they are asking us to write y as a function of x. Right now, y is written as a function of w, right? Because you've got w squared minus 4. And then you can see w is written as a function of x. So what this is going to happen is you are going to take the y function and replace it. Right now it's y as a function of w, but we want to change it where y is a function of x. So technically you are going from y to w to x. So we are going to take this w equals x plus 6, and you're actually going to substitute inside that y function where you have w squared minus 4. So we have y equals w squared minus 4. So we are going to replace that w with x plus 6 because that's what they are giving us. And they are asking us to simplify our answer. So you do want to go ahead and FOIL that x plus 6 squared and then bring in the negative 4. So let me see what you get when you try and simplify this. So have your answers ready. Don't send it in just yet. I want to give everybody a chance to get their answer ready. So have it ready, get it ready to type. And then when I ask you to, you can send it in chat. So not just yet. Okay, go ahead, send your answers in, guys. All right, x squared plus 12x plus 32 equals y. X squared plus 12x plus 32. Okay, let me see. Maya, Hannah, Katie, you guys have 36 instead of 32, okay? Mikhail, x squared plus 12x. Okay, so I'm kind of thinking Maya, Hannah, and Caitlin, you guys didn't do the -4 at the end. Because everybody else seems to be coming up with that 32 instead of the 36. Yeah, okay, that's what I thought. Alrighty, very nice. So yeah, if you go ahead and FOIL this, you know, this will come out to be what you guys have. Okay, x squared, 6 plus 6 will add up to 12x. 6 times 6, of course, is 36. So when you bring that back into our problem over here, you know, that comes out to be your 12x plus the 36. But then when we do that -4 at the end, that's where you guys are getting that 32 from. So this will actually be your final answer. And you can see now our y function instead of w is in terms of x. So this is exactly what composition is. But you know, instead of writing it in that composition format, they're giving it to you as two separate functions. All right, very nice job, guys. So that's our x squared plus 12x plus 32. Okay. Let me clear this out. That was it. Yeah. Did anyone have questions on this one? Okay. So we had talked about operations last time. We did a little bit of the domain. And then, of course, we talked about how the composition of functions work. Now, again, there are obviously some problems that you guys will be working on your own. If there's any part of that that you are having difficulty understanding, you know, reach out to me and we can work on that. So the next section I wanted to talk about is the one that's going to take us a little bit of time. And that's going to be our 2.5, which is talking about the inverse functions. So inverse functions, and again, if you have seen the video lecture, then you have an idea over here. The idea is whatever the first function will do, the second function will undo, right? So if you just think in simple terms, subtraction will undo what addition did, right? Multiplication will undo what division did. Cube root will undo what a cube function did. Now these are single operations, but what happens if you had both multiplication and addition in the original problem? So how would that, you know, undo with the inverse functions? So one of the things that we are always looking for when we are trying to find inverse functions is for the property whether your function is one-to-one or not. And usually when we're talking about functions being one-to-one, you know, we're talking about for one value of X, you should only have one value of Y. If you look at this definition over here for the one-to-one function, you know, we're talking about how no two ordered pairs can have different first coordinates with the same second coordinate. So no two ordered pairs with different first coordinates, that's of course the X value, and same second coordinate. This definition, guys, is a little bit different from the function definition we saw in section 2.1. Here we are saying for the same Y value, you cannot have two different X values. So if you look at this pizza example over here, you can see if we think of X as the cost of the pizza and Y as the number of toppings, you know, there's no overlap happening with the same Y having two different coordinates. And actually here, you will see we are very easily able to switch our X and Y values. We can now make X the number of toppings and Y as the cost. So that's actually what we're looking for in that one-to-one relationship between functions. So if you will look in the middle, I was talking about the dollar menu at, you know, fast food restaurants, because in that case, you can see for $1, you know, you can get maybe fries, a drink, maybe a small burger or a wrap or, you know, something like that. I mean, you can kind of see how the dollar menu is. So for the same $1, you will have 5 or 6 different items that you will be able to buy. So that's not a one-to-one correspondence. If you are paying $5, then you can see you're basically getting a plain cheese pizza. If you're paying $11, then you know you are getting exactly 3 toppings on your pizza. So that's one of those important things we are always looking for whenever we are trying to find an inverse function. We want to make sure, and again, I'll repeat that, for the same Y value, you should not have 2 different X values. That's when our function is not one-to-one, which means we cannot find an inverse. So just some basic examples here again to make sure we are, you know, comfortable with this concept. This one here wants to know if our function is invertible. So that means first we have to see, do we have that one-to-one correspondence between our 2 variables? So this is talking about a function that pairs the number of days since your birth with your age. So just think about it, for the same Y value, can we have 2 different X values? And it doesn't matter which one you take as the X variable, which one you take as the Y variable. So the number of days since your birth and your age, can we have that one-to-one relationship?
Yes.
Yes. Randy, are you saying yes also?
Yes.
Okay. So let's think about this, because this is an example we have used in the past. If somebody is 20 years old, or a bunch of people are 20 years old, are they going to have the same number of days since they were born?
Not necessarily.
Not necessarily. So you know what's going to happen is that number 20 can be the same for a bunch of people, but depending in which month they were born, those number of days are going to be different, right? So that means for the same Y value, you will actually end up with 2 different X values. And in this case, of course, we're taking the Y value to be the age and the number of days to be the X value. So if in either direction that relationship does not work, it's not one-to-one. So this is actually a not one-to-one function, which means it's not invertible. In the second one, we're talking about a function which is again pairing, but this time it's the number of days that you made a deposit of $100 at 6% interest being compounded daily with the amount of interest. So if they're telling you, you have the number of days, let's say, 70 days is what we have deposited this money in our bank account, earning 6% interest. Compounded daily, remember compounded daily means the interest is being broken down and it's being added daily to your account, and the amount of interest, so the dollar amount of the interest you earn and the number of days you have left the money in this bank account. Do you think there's going to be any overlap happening where for the same Y value, we will end up with two different X values? And in this case, you can think about, for the same number of days, will you have two different dollar amounts for the amount of interest?
No.
No. And the other direction would be for different amounts of interest, would you have the same number of days? So if you earn like $50 in interest or you earn $55 in interest, will they have the same number of days?
No.
No, because the reason here is, guys, our money is being compounded daily. Oops. And since the money is being compounded daily, your interest is being calculated on a day-to-day basis. The number of days is always going to be unique with respect to the amount of interest earned. Now, if this was being compounded monthly or weekly, then yes, it could happen that you would end up with the same number of days for different dollar amounts. But because the money is being compounded on a daily basis, the number of days and the amount of interest is always going to give you a unique relationship. So this one we would say is a one-to-one function, which means we can find its inverse and we can say it's invertible. Okay, so let's take a look at, again, some examples here from our homework. Okay, so you know how we use the vertical line test when we were trying to see if we had a function or not? For trying to figure out if our functions are one-to-one or not, we can actually use the horizontal line test. So you will see, again, going back to our definition here, when we are saying for the same second coordinate, you cannot have different first coordinates. Just think about it. If we have a horizontal line, it will have the same Y value, but it can end up having different X values. So for one-to-one tests, we use the horizontal line test. And of course, it's as simple as drawing a horizontal line through your function. And if it crosses your function at more than one point, that means for the same Y value, you have, different X values. Which of course tells us our function is not one-to-one, which means we will not be able to find its inverse. Of course, then we would say it's not invertible either. So just like your vertical line test, the same way the horizontal line test works, it should only cross our function at one point. If it crosses at more than one point, we do not have a function. So what do you think about this guy? Will this be a function? If you draw a horizontal line through that? Yeah, Hannah, I'm seeing you nod, Arthur, Katie. Alrighty, very nice. Okay, let's look at our next one here. And of course, like we had seen with functions, we will not only have just graphs to look at, we will have these equations also that we have to try and figure out if our function is one-to-one or not. So again, falling back to our definition, where we are saying for the same Y, we cannot have two different X values. So the way we do this algebraically, guys, is you actually start out by taking your function and we actually pretend like we are using two different X values and we set it equal to each other. So we use like X sub 1 and X sub 2. So we're pretending that we're starting out with two different X values, But if we can show that x1 is actually equal to x2, then that way we are saying, okay, we pretended like there were two different x values, but they actually are the same x. So our function is 1 to 1. So if we can, at the end, show that x1 is equal to x2, our function is 1 to 1. If x1 does not end up becoming equal to x2, then your function is not 1 to 1. So how this works is on the left-hand side where I have f of x1, I'm going to take my function definition and replace both my x values with x sub 1. So the left-hand side will become 3 minus x sub 1 over x sub 1 minus 10. Same thing on the right-hand side, but now we are using x sub 2. So that would become 3 minus x2 over x2 minus 10. And our ultimate goal, like I said, is to show x1 is equal to x2. So this is where we're going to use algebra to try and simplify this. So the first thing we do, and we've kind of talked about this before, start with cross product, okay? So when you do cross product, let's see, we are multiplying 3 minus x1 with x2 minus 10. On the other side, we are multiplying 3 minus x2 with x1 minus 10. And again, since they are both binomial terms, on both sides, you have to do FOIL. So take it slow, don't rush through this. Let's start with our left-hand side. So for the left-hand side, we've got 3 minus x1 multiplied with x2 minus 10. So remember, that's first terms. So 3 times x2, the outer terms, that's, let's see, 3 minus negative 10 will become negative 30. The inner terms, that's negative x1 times x2. And then the last terms is negative x1 times negative 10. So negative and negative become positive. 10 times x1. Okay, so this is what we're getting on the left-hand side. While I'm here, let's go ahead and multiply the right-hand side also. So that's 3 minus x2 multiplied with x1 minus 10. And you will see it's going to be pretty similar to what we just did. So again, here we are doing 3 times x1 for the first terms. Then we are doing 3 times negative 10, which is again negative 30. Negative x2 times x1, so just putting it in order. And then again, negative and negative is positive. 10 times x2. Okay, so take each side, FOIL it, and like I said, go slow so you don't make a mistake. So on the left-hand side, we had 3x2 minus 30 minus x1, x2 plus 10 times x1. On the right-hand side, we have 3x1 minus 30 minus x1, x2 plus 10 times x2. And what do you think is going to happen here when you try and bring those terms together? Just think about it. If I try to add that 30 on both sides, that 30 will end up canceling out. If I try to add this x1 times x2, so again, that will end up becoming plus x1, x2, and then I add that again over here, plus x1, x2. Obviously, they will also end up canceling each other out. So half of those terms just cancel out, leaving us behind with, let's see, on the left-hand side, we have 3x2 plus 10 times x1. And then on the other side, we have 3 times x1 plus 10 times x2. Okay. All right, now what do you think you will do to try and simplify this further? You have 3 times x2 plus 10 times x1 on the left, 3 times x1 plus 10 times x2 on the right hand side.
You'd combine the like terms.
Yeah, exactly. Combine your like terms. Very nice. So let's go ahead and subtract this 3 times x1. We'll bring it over here to the left. So, of course, that ends up canceling out from that side. And then we'll do the same thing with our x2, and let's subtract 3 times x2 from here and move it to the right-hand side. And again, these guys cancel out on the left. So when we add what's left behind, you've got 10 minus 3, right? Which would be 7x1. Same thing on the right-hand side, 10 minus 3 is 7, x2. What else can we do over here, guys? Because remember, our goal is to show x1 equals x2.
Can we divide by 7?
Yeah, exactly. Very nice. Divide both sides by 7. And obviously, just the 7s cancel out. And this is kind of what we were hoping for. You have x1 equals x2. And if we can show this, then we know our function is 1-to-1, which means our function is invertible. So algebraically, it definitely takes a little bit of calculation, and I picked this example because this one definitely takes a little bit more calculation to kind of get to that final goal. Some of the other examples you will see are actually a lot more easier to work through. So this one is probably the one you're going to need to, like I said, have a little patience, go slow, and you will be able to come up with your answer. So let's go ahead and put that answer in. So we know this function is 1-to-1 because x1 is equal to x2. And there we go. Question on this one, guys? Okay. No question so far, all right. Let's take a look at all right, so now we're actually getting into finding our inverses. So as you can see, they are saying if the function is invertible, find the inverse. So going back to the definition, we said for the same y, we cannot have two different x values. So looking at this ordered pairs, the list of ordered pairs, for the same y, do we have two different x values? Yeah, Arthur, you're saying yes? And this is right here in the middle, right? For the same y value, you can see we have two different x values, right? So this is actually not 1-to-1. And since it's not 1-to-1, our function is not invertible. Everybody okay with that? Yeah? Okay. Again, look at the ordered pairs. For the same y, do we have two different x values? No? Katie, Arthur, I'm seeing you guys say no. Yeah, because you can see, there's three ordered pairs, right? And your y values are 5, -6, and 9. So we're not seeing any repetition happening in our y values. So we know this guy is definitely 1-to-1. So if it is 1-to-1, then, of course, we can find its inverse. Okay, so when you are actually finding the inverse, kind of like we looked at the pizza example in the handout, you literally just switch your x and y values. And that's really interesting. With ordered pairs, you're literally just switching the x and y values. But that's kind of the same thing we'll be doing if we had equations for these functions. So if you just think about this, if you are going to switch the x and y values, then the domain of the original function actually ends up becoming the range of your inverse function, and the range of the original function ends up becoming the domain of your inverse function over here. So let me, before we answer this, let's go back to our handout over here. And we are talking about this right over here. So we are saying since the coordinates in the ordered pairs are interchanged, the domain for the inverse function is the range of the original function, and the range of the inverse function is the domain of the original function. And you should notice that we use this little notation when we are talking about the inverse function. So you read it as f inverse. So it kind of looks like you're putting a -1 exponent, but that's the notation we use for inverses. So anytime you put that little -1 in the exponent, we're actually talking about the inverse function. So it's not really an exponent, just the notation that you use for your inverse functions over here. So yeah, kind of keep that in mind, how those domain and range basically end up switching places from the original function to the inverse function. So now, since you just have to literally interchange your ordered pairs, what do you think these ordered pairs will be for our inverse function in here?
5, 3, -6, 6, and 9, -5.
Yeah, very nice. Exactly. Just switch that order. So 5 and 3, comma, -6, 6, again, comma. And you know, of course, you're typing each one of these as ordered pairs, so make sure they're each individually in parentheses, and then 9, -5, and that's it. And then now they are saying go to the inverse function and find the ordered pair where your x value was -6. So what will this answer be here?
6.
Yeah, because you're looking at this ordered pair right over here where your x value is -6. So its corresponding y value is +6. Very good. And the last one, you will actually see they're asking us to do a composition. And they are saying take the, whoa, there we go. Take the inverse function, compose it with the original function at 6. So basically what we have is f inverse on the outside and then f of 6 on the inside. So what we did in the last section, so we'll start with f of 6. And what is f of 6 if you go to the original function? What's your ordered pair going to be for f of 6?
-6.
Yeah, -6, because you're looking at this ordered pair. If f is 6, the y, or sorry, the x is 6, so the y would be -6. So that means when we come back over here, instead of f of 6, you're going to replace it with -6. And then go to the inverse function now, and what do we get as our answer?
What do we get? +6?
Yeah, because you just did that over here, right? That's basically the same answer. So what's happening over here, guys, if you look at the composition, we originally started out by using 6 as our x value. By the time we finished our composition calculation, we ended up with that same answer, 6, right? So this is actually what happens every time you do a composition between the original function and the inverse. The number for the x value you started out with, that's the same answer you end up getting as your final answer. So the composition between And let me go ahead and finish this one here. Number 6. Okay. And let's go back to our handout quickly. So if you actually take, let me see, where did I write that down? I thought I had it written down. I'll need to see where I have it. But basically the idea is when you actually take the composition between the inverse functions, you always end up getting an identity function. Let me see where I have that. Oh, right over here. So anytime we end up taking these compositions, basically this is kind of what we just got done talking about. So anytime you take a composition, and it really doesn't matter what the order of your composition is, if these two functions are inverses of each other, you are actually always going to get the identity function as the result of taking this composition. And remember, the identity function is where both your x and y values are always going to be the same. So they have ordered pairs like 1, 1, 2, 2, 3, 3, or -1, -1, -2, -2. So they are always going to be whichever x value you started out with, that's the same. You're going to end up with your y value when you do these ordered pairs. And that's kind of what this last example here just highlighted for us. All right, so that was looking at a set of ordered pairs, how you can find the inverse function, and when you do a composition, what that would end up looking like. Now let's take a look at this one over here. And this is another really interesting thing I like about these inverse functions, is you will see in this example over here, they are actually using this little dotted line. If you look at the equation for this dotted line, it is actually that identity function, y equals x. So you can see all of these ordered pairs would be 1, 1, 2, 2, 3, 3, 4, 4, right? So all of those would be the identity. So the idea here is when you are looking at the graphs of your two functions, they should actually be reflection with respect to that line. So imagine if you were to fold your graph along that dotted line for y equals x, are your two halves going to coincide? Are they going to be overlapping? So is it a reflection for the two graphs when you look at this function over here? So with respect to the dotted line, are the two halves reflections of each other? Okay, let me show you the next example and then you tell me what do you think. If you fold along that line, will the two halves coincide with each other? Or basically, the other way to look at it, and remember we had done this with our symmetry example last time. If you take a point on the line and if you do the distance, will this distance be the same as this distance over here? If we do that same thing in the previous example, if you pick a point on the line, is this distance going to be the same as this distance? No, right? I mean, it's pretty obvious that one distance on the top is a lot smaller than the one on the bottom. So if you use the idea of distances, if that's better than to visualize if the two halves would be reflections, if the distance is not the same, then it's not inverses of each other, which means these two are not inverse functions. So this guy would be a no. But if you look at this guy over here, and again, you don't have to go, you know, too far out. Let me make this guy bigger. Okay, so just pick the origin as your point and look at the distance from here to here. Does that look about the same? Yeah, and that's going to be true throughout the graph, right? You can do it, I don't know, from this point over here. So you can look at the distance from here to there, or from here to there. You can do it at the other side here. Look at the distance from here to here, and you will see it's always going to end up being the same distance. And in this one, it's actually even easy to visualize, right? If we fold along that line, we can see how the two apps will exactly coincide with each other. So for this function, you know, we would definitely say, yes, these are inverses of each other. So just a different kind of, you know, what happens with when you're looking at these graphically, you know, how to come up with the inverse idea. So even with graph, always use that diagonal line y equals x to try and see if the two halves would be reflections of each other, or the distance from that line to the graph would be the same or not. So just some of those brief examples, but now let's see how we can find our inverses over here. So there's two different ways I'm going to show you of how to find the inverse. And honestly, you will need to practice to see which one you think works the best for you. So the first method is what we call as the switch and solve method. So in this case, we're going to start with our original function, but I am going to start by replacing my f of x with the y variable. So I'm actually going to write it as y equals 4x minus 6. The switch is basically where we are now going to switch our x and y variables. So we're going to do a little interchange over here. So instead of y, I'm going to write x, and instead of x, I am going to write y. And the solve is you want to get y by itself now, right? So move everything else to the other side. So we would start by adding 6. That will cancel out on the right-hand side. We end up with x plus 6 equals 4y. And again, to get y by itself, divide everything by 4. So now you have y by itself. We have x divided by 4, or if you want, you can write it as 1/4 x plus 6 divided by 4. It's a fraction. So make sure you're always reducing your fractions. You know, in this case, that becomes 3/2, right? And that's it. Replace the y with your inverse symbol. So that's the switch and solve method. We start by switching the places of x and y, and then you're solving to get y by itself. So our inverse function is going to be 1/4 x plus 3/2. So that is actually the method that, you know, would be more of the algebraic way, but you can also actually solve this, what we call it, as mentally. So let's take a look at that. Again, your original function was f of x equals 4x minus 6. I'm just replacing the f of x with y. So the way the mental method works is you start with your variable x, and you see what's the first thing you are going to do. So if I gave you x equals 0, would you multiply by 4 first, or would you subtract the 6 first from your x value? Arthur?
Multiply by 4 first.
Yeah, you would multiply by 4 first. Very nice. So that means the first thing we are doing is multiplying our x value by 4, and then we are subtracting 6, right, from that answer. So the way the mental process works, guys, we're still going to be using x as our variable, but since you subtracted 6 last, with the inverse function, and this is for the inverse function, you are actually going to add 6 first, which means we are going to do x plus 6 first. So we always go basically in the opposite direction, and you reverse the calculation. So subtraction becomes addition. We multiplied first, which means we are going to divide last, and then you divide by 4. And that's the exact same answer we had, because now if I just separated this, I will have my 1/4 x plus my 3/2. Or if you want to leave it in this form, you can leave it in that form also. So it's up to you. And we could have, obviously done that over here. Let me change the color. When we divided by 4, you could have done that over here also if you did not want to separate it. So either as 1/4 x plus 3/2 or x over 4, x plus 6 over 4. I'm actually not sure which, do they have a preference or are they okay with both? Let's try the first one. So we've got x plus 6, and we are dividing that by 4, and let's check, what this guy says. Okay, so it looks like they don't really need you to separate your denominator in this case. They will accept a single denominator. Because with my math lab, it's always hard to tell which format they're going with. So you have the switch and solve method, and you have the solve mentally. And you can see in this particular example, both of those methods work. But then you can actually have examples like our next one over here. I think it's the next one. Yeah, this one, the mental process really does not work because you have x on the numerator, you have x in the denominator. On the numerator, you've got multiply by 2, add 7. On the denominator, you've got multiply by 9, add 4, and then of course there's that whole fraction thing happening. So for this example, I recommend only the switch and solve method. So let's take a look at this guy here. So in this case, again, I'm going to start by replacing my f of x with y. So we will have y equals 2x plus 7 over 9x plus 4. And remember, again, we're using the switch and solve method. Okay, so once you have this, now interchange the x and y variables. So the y becomes x, and both numerator and denominator, the x will become y. So you should have x equals 2y plus 7 divided by 9y plus 4. Everybody with me so far? Okay. So now, the idea is we're solving, which means we need to get the y by itself, move everything else to the other side. So technically, since I have y in 2 locations right now, the first thing we have to do is find a way to get those 2 y's together. So the first thing we will actually do is go ahead and multiply by that 9y plus 4 on both sides of our equation, because we want to get rid of that fraction. So we are multiplying both sides. I should have left a little space on the left, but basically you're multiplying both sides by 9y plus 4 on the right hand side. Of course, the denominator will cancel out. So we have x times 9y plus 4 on the left hand side and 2y plus 7 on the right hand side. Now you will go ahead and distribute that x inside the parentheses. So this will end up giving us 9 times xy plus 4 times x on the left. Of course, 2y plus 7 on the right. And now we're actually getting close because we have kind of brought that y, outside of the parentheses. So we want to try and bring both the y terms together. So in this case, and it doesn't matter which one you move, but I guess I'm going to go ahead and subtract my 2y on both sides. So let's see, we will end up with, you know what, while I'm actually here, let's go ahead and move that 4x to the right-hand side also. So on the left-hand side, you should only be left behind with 9xy minus 2y. On the right-hand side, we should have minus 4x plus 7. So all the y terms are now on the left-hand side. The ones that don't have y are on the right-hand side. Now, remember, our ultimate goal is to get y by itself because we want to get the y, move everything else to the other side. So from both of these terms, I am going to factor out that common y, bring it outside as your greatest common factor. You have y on the outside. On the inside, we are left behind with just the 9x from the first term minus 2 from the second term. Do we see that, guys? Anybody have a question up until this point? Of course, your right-hand side will stay the same, minus 4x plus 7. Now what will you do to get that y by itself since you have 9 times 9x minus 2? How do we get that y by itself?
You'll subtract 9x from both sides.
Nope.
Oh, would we divide both sides by 9x minus 2?
Yeah, because we're multiplying, right, Brandy? You've got y multiplied by the parentheses, 9x minus 2. So since we want to get y by itself, you're actually dividing both sides by that whole parentheses, 9x minus 2. So those guys will cancel out. And now we have isolated the y. He is by himself. And then we have minus 4x plus 7 divided by 9x minus 2. And then, replace that y with your inverse notation. So that would become f inverse of x equals minus 4x plus 7 divided by 9x minus 2. And this is kind of what I was talking about. This is impossible, or I have not been able to figure it out because I've tried to do this mentally a couple times and it just makes my brain hurt. So I usually do not recommend using the mental method unless you are confident that you will be able to get it to work. I recommend using the switch and solve method for these types of examples over here. Alrighty, so that was, once you isolate the y, then you're basically just replacing it with the inverse notation and you are done. So let's type this in. Negative 4x plus 7 is our numerator. And then we're dividing that by 9x minus 2. And let's check that answer. Question on this one? And you actually have an example similar to this one that we just did in your video lecture also. Let me clear this out. So you should actually have that when we do the switch and solve method. Oh, this one right here, number 13, is very similar to what we just got done talking about. So you do have an example similar to that in your video lecture also. Now let's take a look at our next example over here. So how about I give you guys a couple minutes, and why don't you give it a try? You can use the switch and solve method. You can use solve it mentally if you're comfortable with that, and then we'll go ahead and discuss the answer. But let me see what you come up with on your own. And again, just have your answer ready. Don't send it in the chat till I ask you to. Remember, again, start by replacing the f of x with y. So you should have y equals cube root on the whole thing x minus 8. And then, you're doing the switch, right? To replace the x with the y with the x. Then the idea is, how would you get rid of the cube root? So think about that. If this was, you were solving for a number, how would you get rid of your cube root? That's the same process you have to use over here. Once you get rid of the cube root, then it would be a matter of getting y by itself. To take it step by step, first start by replacing f of x with y. Once you get y equals cube root of the entire quantity x minus 8, then switch your x and y values. And then the idea is you're trying to get y by itself. So then you have to get rid of the cube root and then get y by itself. If I tell you any more, I might as well just solve the problem for you. So I'm going to give you a little bit of time. Okay, guys, go ahead, send your answers in. All right, let me see. So you've got x to the third power plus 8, x to the third power plus 8, x to the third plus 8. Okay, seems like most of you have that cube root of x plus 8. Okay. Wait, and I guess you're missing a third in that. Okay, alrighty. So yeah, looks like everybody came up with that. Very nice. Great job, guys. All right, let's do a quick calculation. So I'm actually going to show you the switch and solve first, and then I'll show you the solving it mentally. Like I said, we start by replacing f of x with y, cube root of x minus 8. Then we do the interchange, so x on the outside, y on the inside. And then, of course, whenever we are getting rid of a cube root, we have to use the cube, right? The third power. So you raise both sides to the third power, which helps us cancel out the cube and the cube root. So that ends up giving us x to the third equals y minus 8, and then get y by itself. Move that 8 to the other side, and very nice. You have x to the third plus 8, which is our inverse function. Okay, so switch and solve method. Now, if you wanted to solve this mentally, our original function. Okay, so again, if you look at the x, the first thing we would have to do to the x is subtract 8, right? Let's say if I gave you 8 as the x value, we would first subtract the 8, and then whatever answer you came up with, you would end up taking a cube root on that answer. So when we talk about the inverse function, with the x value, you know, we have to go in the opposite direction. So since you're doing the cube root last, we would have to do the x cubed first. And then since we subtracted 8 first, we would have to add the 8 last. So your inverse function would again end up becoming x to the third plus 8. So either mentally or the switch and solve method, whichever one you are most comfortable with. I would say practice with both and see which one you take to. So that's x to the third plus 8. There we go. Did anybody have a question? Were all of you okay with this example? Yeah, alrighty. So let's clear this guy out. And alrighty, so here they're actually going to that idea of what happens when we do compositions. So they're asking us to find out what will happen if we do f of g of x, or if we reverse the order and do it as g of f of x. And they want to know if they will in fact be inverses of each other or not. So let's start with the first one. And I guess I'm going to do that over here. We are given f of g of x. So you can see g is the inside function. So that means we're going to be taking this entire g function and putting it inside of the f. Remember that example we did with the y, the w, and the x in the last section? This is kind of that similar type of example. So you're taking the entire g function, and like I said, you're putting it inside of the f, which means where you're seeing that x for the f function, we're going to be replacing it with the g function. So we're replacing. So I have 6 on the numerator, x minus 4 on the denominator for my f function. But in the place of x, I am actually going to be replacing it with this whole entire thing. So you are going to have 6. There we go. So this guy should be 6 over x plus 4. So like I said, literally replacing that x with this entire g of x function. And now we have to clean this up. Okay, so let's take it step by step. So we are right now given 6 divided by 6 over x plus 4, and then we can bring that minus 4, right? And then as you can see, our plus 4 and minus 4 will just end up canceling each other out. So we are left with 6 divided by 6 over x, right? Now remember, since we have a fraction in the denominator, what you can do is keep that numerator 6 as it is, but then we invert the denominator, and remember, you end up multiplying whenever you invert your denominator. So since we are taking 6 divided by 6 over x, you know, and if it helps, you can think of this guy here as 6 divided by 6 over x, which is basically changing when you invert the denominator, division changes to multiplication. And then since you have 6 on the numerator, 6 in the denominator, they will cancel each other out. And you, of course, just end up getting X as your answer, which is what we want, because if you remember, I had told you, when you take the composition of your two inverse functions, you get the identity function, right? So you should only end up getting X as your answer. And we did. So that's a really good sign for this example over here. So for the first part A, we can go ahead and type that X in. Okay, so that part looks good. And now they're actually asking us to reverse the order. So let me go ahead and clear all of this out. Okay. So we still want to figure out if these are inverses of each other or not. And for that, we should get the same result if we change the order of our composition. So what happens if we now do G of f of x? Which means now we are going to be taking the entire f of x function and putting it inside of the g function. So g on the outside, f of x on the inside. So we have 6 divided by x and then plus 4 on the outside. And we are again replacing our x over here with the entire f function. So that's 6 divided by x minus 4. So let's see how we can clean this guy up now. So this one, and I think I'm gonna have to make a little room over here, but right now we have 6 divided by this fraction, 6 over x minus 4, and then you have that plus 4 at the end over here. So you know what, let's get rid of this guy, let's get rid of this guy, and make some room over here. Okay, so let's take a look now. So again, we have, if you just look at this first part over here, we have the same thing where you have a number on the top being divided by a fraction. So for that portion, again, we can go ahead and say, okay, I have 6 on the numerator, and then I can change my division to multiplication by inverting the fraction. So you can put x minus 4 on the top, 6 on the bottom, which is the exact same thing we did over here on the right-hand side when we were simplifying that last part. So we're doing the same thing over here, and then you, of course, have that plus 4 at the end. So we'll just leave that guy at the end. So 6 on the top, 6 on the bottom will end up canceling each other out again. And you end up getting x minus 4 from the numerator that's left behind, the plus 4 from here, and again you will notice plus 4 minus 4 will cancel each other out, and again we ended up getting the answer x over here. So again, if you can again show that you get an identity result, then we know these functions are going to be inverses of each other. So if we can get x as the answer for both, we actually do have inverse pairs of each other. So you can see I have x on the first composition. When we reverse the order, we also have x as our result on the second composition. So when both of them are x and x, we will say yes, they are inverses of each other. And that's the last part you got to do. Okay. And I think that was the last one on this guy. So again, if you go back, oops, sorry, didn't mean to do that. Okay. So here you have the procedure for your switch and solve method. So anytime you're not sure, how to do that order, you can definitely look at your handout over here. We talked about, this was the last example we just did, how when you take the inverses of each other, you should always get x as your answer, which is your identity function. And if that happens in both directions, then you have inverses of each other. So it has to work in both directions. And then this is what I had talked about earlier. When you look at the graphs of these functions, they should always end up becoming reflections of each other. So I actually very quickly just wanted to show you, let's take a look at this example over here. You can see our original function is f of x equals square root of x plus 2. So if we talk about finding its inverse, right, we can again try and do this mentally because this is very similar to that cube root example we had seen. You can see with the x function, we first add 2, then we take a square root on top of the whole thing. So when you do your inverse function, of course, we would have to start with x. Since we did the cube root function last, we would actually have to do the square function first if you go in the reverse order and reverse operation. So for cube root, we would have to do the square. And then since you are adding 2, we would have to subtract 2. Now, what's going to happen here, and let me show you the graph for this x squared minus 2 function. Let's get rid of this guy. And let me open my Desmos. So as you will see, when we do our little x squared minus 2, this looks like a parabola, right? And we know it's going to fail the horizontal line test because if I draw a horizontal line through this, it's going to cross at 2 different points. So remember we were talking about how the domain and range switch places for the original function and the inverse function. So what's going to happen over here is if you actually talk about the domain for our original function, you can see with that square root of x plus 2, we cannot have any negatives inside of our square root, which means the smallest number is going to be what? For our x value when we talk about the domain for that f of x function. What is the acceptable smallest x value here? So that I don't end up with negatives.
0.
Okay, if we did 0 plus 2, you would get positive 2. Can we go lower than 0?
-2.
Negative 2, yeah, because when you do negative 2 plus 2, that will actually add up to 0, right? Which will still give you a positive number. So the smallest x value I can have is -2, including -2, right? And so we know if we use -2 as the smallest x value, then the smallest y value we will have is going to be 0, right? Because it will be -2 plus 2 is 0. Square root of 0 is 0. So your range will actually go from 0 to infinity. So what's going to happen over here, guys? The range will now actually become the domain of this inverse function, which means the domain for our guy over here is going from 0 to infinity, including 0. And the range is now the domain of the original function, which will end up becoming -2 to infinity. So when we say domain is going from 0 to infinity, that actually means, let me get this over here. That actually means you are ignoring this entire graph on the left-hand side. All of this is actually not going to be part of our graph because you're only starting at 0 and going to positive infinity, right? So if you imagine that left-hand side is not there, then our function will pass the horizontal line test, right? Because now our function will only cross at 1 point. So what's going to happen is we are going to have to restrict our domain and say domain only goes from 0 to infinity. And you will see, on our range value, it's definitely coinciding at -2. Oops, I shouldn't do that because I will change this. So we will say range is now going from -2 to infinity because you start at -2 and you are going up towards positive infinity. So this happens a lot of times with these parabola type of equations. You always have to restrict your domain if you are going to be able to find your inverse function, because if we keep the entire domain what the original function has, for these parabolas, we will not be able to find inverses. So a lot of times you will see that we always end up talking about restricting our domain. And let me clear this out. So you will see even for this function, we are saying only for x values from 0 to greater than 0, and then you can find its inverse to be just the square root of x function. And something similar will actually happen here in example 18 also, and you can see that in your video lecture. So any questions on these inverse functions? And this last page is actually a great exercise if you want to get used to doing these inverses mentally. You can kind of look at these examples on the last page to help you out. But again, I will reiterate the fact, guys, for examples like number 13, use the switch and solve method. Okay, and then actually, we're not going to be doing this section, but I just wanted you to show. I guess I should have opened that, but I did not. This is an optional section. We don't really talk about this guy. But this is actually where we talk about variation. And the reason we're not doing variation, because the idea is you guys should have seen that maybe in a previous math class, so they didn't want to have redundancy. But when we're talking about variation, we're just talking about what kind of behavior your x and y variables can have. So when we talk about direct variation, we're basically saying if one variable is getting larger, the other one is also getting larger. So if x gets bigger, the y also gets bigger, and that usually happens when you have equation in this format. So where k is a constant number, so you can kind of think of our y equals mx plus b format, except your b is 0. So the idea is if x value is getting really large, the y value also gets large. If x is getting smaller, your y is also getting smaller. So that's what happens with direct variation. And you can kind of think of like with this example, if you buy a bigger size smoothie, you end up paying more money, right? If you buy a smaller size smoothie, you pay less money. But then we have inverse variation, and as the name suggests, with inverse variation, if one quantity is getting bigger, the other one's actually getting smaller. So you can see we're talking about the Concorde versus a Boeing 747 airplane over here. So the idea was Concorde would fly at a faster speed than Boeing did, which they have decommissioned Concordes now. Those planes are not being used anymore. But the idea was if it's flying at double the speed, it would take you less time, right? Which means the speed increased, but the time went down. If the speed decreased, then your time went up, right? So that was that inverse relationship. And look at how different this equation looks, because now instead of multiplying k and x, you are actually dividing k by x, right? So this is what created that inverse relationship between your variables. Then you can also have joint variation, and joint variation is where you have more than two variables. So you've got x, y, and z. And so in this case, of course, two quantities go up, the third one would also end up going up, because this looks very similar to our equation for direct variation. So at that meant all three of the quantities were growing together or decreasing together. So hopefully, the idea was basically that you should be comfortable with these different types of variations. Combination or the combined variation basically means you can combine inverse, direct together into the same aspect. So you can see how that relationship ends up looking like. So it's kind of like you have one variable that's being multiplied, one variable that's being divided. So this is a combination of both inverse and direct variation put together. So I just wanted you to kind of be aware that you do actually have this section on variation. Even though we are not officially talking about this, this should be something you should be aware of. So I would say just look through the handout, you know, because whatever math class you end up taking up next, we'll make the assumption again that kind of like we did, that you have done variation before and you are comfortable with it. So I do have these handouts posted in D2L for you guys as a reference. So just kind of keep that in mind. But you know, no homework on 2.6, no exam being asked for 2.6. So don't worry about that section on variation. That's just for your information. 2.1 to 2.5 are the only sections we are working on. So you should have all the deadlines in my math lab, which will be for the 30th, Wednesday. So like we did last time, 2.5 exam can be a little bit longer because this is a little bit, again, bigger section, right, with the 5 sections in there. So again, we're going to be using the entire class time as exam time. It's actually, I think, exam 4 and 5, which are the smaller exams. Exam 1, 2, and 3 are the bigger exams for us. So we are definitely I'm going to give you guys, again, the full class time. I want to make sure you have enough time to work on your assignments. So same setup like you had last time. So just please make sure you're working on all 5 homework sections, the quiz, and again, if you want to use the practice for testing purposes, you can use the practice exam also. So any questions popping up before I dismiss you guys? No? Everybody's feeling comfortable? All right, wonderful. So Hannah, I'll be seeing you on Wednesday, and then the rest of you guys, I'll see you about 11:01, 11:02. Okay. All right, everybody, take care, and I'll see you in a little bit. Bye, guys.